Okay. Hi, everyone. Thanks for coming to our presentation. I'm Jeff Booher-Kaeding. I work at ARM as a systems architecture engineer, and today I'm here with...
David, I am working at 9elements as a firmware developer.
So today we'll be talking about coreboot on server class ARM hardware. Specifically, we're going to be showing off a proof of concept and reference code. So we'll also be talking about the state of the problem, the biggest challenges that we face implementing coreboot on ARM, and our work to sort of close that gap. So if you want open source firmware on an ARM platform today, you really only have two options. The first one is EDK2, Tiano Core EDK2. It's really the #1 option. The vast majority of servers today run EDK2, and it implements or exposes UEFI, ACPI, SMBIOS. And for better or for worse, UEFI is sort of the firmware interfaces for OSs. Whether it's Linux, BSD, Windows, ESXi, they all more or less work with or expect UEFI. EDK2 is the main open source implementation of UEFI, and it's a successor to traditional BIOS. It has all kinds of features for extensibility. It has features for support for file editing, full network, a shell and a console. And so, depending on who you ask, you might see EDK2 as an operating system itself. And some of these customizable and extensible features can also be a downside for EDK2. You might have a network driver that needs to be written separately for EDK2 than the Linux kernel, and that code may be lightly tested. It may not has as much scrutiny as a Linux kernel driver. And also sort of a downside is that that has led to vulnerabilities being found over the years, and it's really the only option you have on an ARM server today is to boot using EDK2-based firmware. Now, there is an alternative sort of firmware stack approach called LinuxBoot. It was founded a couple of years back to remedy some of the pitfalls that we're seeing with BIOS, traditional BIOS and EDK2 by using a Linux kernel as your normal world firmware component. This meant that you would be able to reuse drivers, you would be able to kind of do all of your normal firmware things in a Linux kernel. But on ARM, up to this point, you would still have to rely on EDK2 in order to generate your ACPI, your SMBIOS, and there are actually some required UEFI runtime interfaces. And so, although we call this an alternative, if it still relies on EDK2, is it truly an alternative? So previously, to enable LinuxBoot, we took an approach of loading LinuxBoot on top of EDK2, and it served as sort of a good first stepping stone towards creating that alternative. We moved away from the sort of monolithic EDK2 UEFI stack, and we prototyped it on a few platforms that we chose for their ease of access to both developers and tinkerers, specifically the SBSA Ref QEMU, the Raspberry Pi, and our ARM Neoverse fixed virtual platform. We use this sort of pathfinding, discovery mission, prototyping, whatever you want to call it, to pencil out the requirements, the firmware interface requirements that you really need on a Linux boot server to boot a standard Linux operating system on ARM. So, and then this EDK2 plus LinuxBoot approach was also used by Ampere to create their Mount Jade platform with LinuxBoot support. That platform is also OCP accepted and offers open source EDK2 and OpenBMC firmware. You might have caught me saying that we have some required UEFI runtime interfaces earlier, and that is because at this point, the only way to convey an ACPI table in ARM onto the Linux kernel is through the UEFI system table. x86 has a legacy way that they can convey this to the Linux kernel, but ARM does not. The kernel maintainers have been fairly clear that if you want ACPI on ARM, the way you have to pass it is through the UEFI system table. And so this means that we also need to implement some runtime interfaces, and if they're left null, it can and probably will crash the system. But the good news is that a lot of these services don't have to be fully implemented. They can just return unsupported. And so now that we sort of have an understanding of the problem, the question is, how could we fully eliminate EDK2 from the puzzle? Could we create sort of a true alternative stack? The first thought you might have would be, well, why don't we just change the Linux kernel? Let's just completely cut out UEFI. Maybe we'll pass flattened device tree with the ACPI pointers. This might be a good idea, but it's very unlikely the kernel maintainers will agree with you. And they've made it very clear that if you want ACPI on ARM, you need to pass it using the UEFI system table. Second idea may be, okay, well, if we continue on this easiest path first for trying to do this feature enablement and discovery, why don't we just look at something like UBoot? UBoot has a very well-tested and fairly good implementation of UEFI runtime services. So what if we just add that on top of our coreboot to implement these runtime services? It's worth a shot looking at, but there's a lot of overlap between coreboot and UBoot, so maybe not the best idea. And then finally, we thought about, what if we create a shim layer that just can expose these UEFI services that we need, the minimum to convey ACPI, SMBIOS, and then return unsupported for all of the runtimes that need to be there, but don't have to be there for Linux to run, I should say.
Thanks, Jeff. So let us get to the technical implementation. We developed our firmware for two different targets. The first one is QEMU's SPSA web machine. So for those of you who don't know QEMU, QEMU is an open source emulator for various architectures, like ARM64, x86. The emulated machine supports SPSA hardware like generic timers and watchdogs. Our second target is Neoverse FEP by ARM. Neoverse FEP, on the other hand, is a full-blown simulator for complete ARM systems. It is commonly used to develop firmware before hardware is even ready. Oops. So first, let us look at our firmware stack from a higher level. ARM-trusted firmware is the very first component in our chain. It supplies the OS with runtime services, such as a secure monitor. Once TFA is done, it passes control to our next component, which is coreboot. As you can see, it is responsible for generating and passing various tables to the operating system. The UEFI stub then comes next. It leaves behind UEFI runtime services needed for the operating system to boot properly. The last stage of our stack is a LinuxBoot kernel, which finally KXX into our operating system. And now, let us take a look at all those components in detail. TFA is ARM's reference implementation for a secure world firmware. It initializes secure world and provides various services to the upper software layers. One example of such a service would be the power state coordinate interface, which is, for example, needed to bring up secondary CPUs. After TFA ran, one could technically already jump into an OS. So at this stage, we didn't face any challenges since we didn't modify TFA in the first place. So probably most of you already heard about coreboot. Coreboot is a lightweight, free and open source implementation of a BIOS for modern computers. It supports multiple architectures, with ARM64 being one of them. Its functionality overlaps with TFA, but in our case, we are only using it to generate ACPI and some BIOS tables, so we should be fine. At this stage, we already faced our first issues. A major issue was to run coreboot after TFA. But why? So coreboot wasn't designed to run on anything else than the highest privilege level, which is EL3. But TFA drops to EL2 as soon as it exits, meaning coreboot would run on EL2 instead of EL3, and therefore also accessing EL3 control registers. So for those of you who are already familiar with ARM64, you already know that this behavior is pretty bad. Accessing control registers that are out of your privilege level will crash the firmware instantly. So we had to avoid that and use the appropriate EL2 registers instead. Furthermore, we had to work on coreboot's ACPI subsystem. There we added support for 64-bit pointers and updated various existing tables. We also added a new table to coreboot, the PPTT table, which simply stands for Processor Properties Topologies table, and is responsible for describing the relationship between CPUs and caches. For SMBIOS, we had to add support for the ARM64 caching architecture, and also we updated existing SMBIOS entries. As mentioned before, our first approach was to use U-Boot for its UEFI interfaces, as it is a well-known and reliable open source firmware. But it is lacking support for 64-bit SMBIOS, and furthermore, U-Boot is designed to work on top of device trees, which is not what we want at all. But most importantly, U-Boot is still a full-blown bootloader, and we don't need most of it since we already have TFA and coreboot. So why don't we reduce this to a minimum? The UEFI interfaces. We can simply extract the UEFI interfaces from U-Boot and make it a standalone layer. Our working name is the UEFI stub. This way, we reduce code and become even more lightweight. We can even upstream it directly to coreboot since it would be based on the payload. Also great is that we would be still compliant to the LBBR spec. So we grabbed the UEFI code from U-Boot and reduced various boot services. Since Linux doesn't use many of them, we also don't need a full-blown console. So we reduced the UEFI console to its essentials, which is printing. Furthermore, we were able to get rid of many other UEFI components, such as the event system, network, capsule updates, and even more. Finally, arrived at our last stage in the chain, the LinuxBoot kernel. In our case, we are using a custom compiled Linux kernel in combination with a U-Boot user space, which then KXX into our actual operating system. In the next chapter, Jeff is going to tell you a bit more about the future of this project. Thanks.
So the first thing I wanted to talk about was our contributions. So a lot of this code is in the process of being upstreamed. Some patches are already upstreamed and merged. Others are still waiting review or are being merged in the next coming, or uploaded in the next coming weeks. There have been various changes to coreboot to support AR64 with ACPI, support SMBIOS as mentioned. And then the UEFI stub will be targeting the payloads for coreboot, we'll be targeting a coreboot payload. And then at ARM, we're planning on hosting scripts and documentation in order to make this easily reproducible on our public GitLab, as well as adding this to the OCP GitHub. And then we wanted to also talk about sort of call to action and next steps. So we're going to use this approach of firmware without EDK2 to refine our LBBR spec, our firmware recipe in our boot-based requirement document. And then there's also an open investigation to look at the UEFI payload package that could give you support for booting Windows and ESXi on top of this firmware stack. It could also potentially remove the dependency for this shim layer altogether, and you could generate ACPI and the UEFI runtime services exposed to the final operating system above LinuxBoot. And the last thing we would like to show you is a demo. So while we take questions, I can put up a demo. It's gonna be. Is there any questions?
Hello, folks. Thanks for the presentation. Has anyone ever thought about using U-Boot directly on servers?
Yes, people have thought about it. I think the problem is that, again, it relies heavily on device trees internally, and that's sort of just not a language that is spoken on servers. Furthermore, there's not ACPI support in U-Boot on ARM at the moment, so that's sort of a few of the reasons.
The device tree support in U-Boot is internal, so it doesn't really matter. I mean, it's on x86 as well. So I don't see that as an issue. The ARM support for ACPI, it'd be pretty trivial to add because it's all broken out at this point. So I definitely think it's worth a look because it can boot, directly from reset. You get everything you need, and you're not having to do all these different steps. Can you go back to after your demo? I'd love to see the diagram again.
Which one?
A diagram of the stack. Is that it? Yeah.
Yes.
There's a lot of bits in there, isn't there?
A lot of what?
Pieces.
There's a few pieces, yeah. So again, I think this is sort of a proof of concept, right? We're trying to just prove out that we can make this happen without ADK2 on ARM. We can meet both the OSVs where they're at, as well as the hardware vendors where they're at. So, because both sides can be a little rigid at times, so.
I had another question. Yes, what is the size? Is it when you integrate, are you getting larger size than ADK2 or getting a little smaller size?
I think it depends on if you're talking about before having the Linux boot kernel or not having the Linux boot kernel in here. I believe if you do not include the Linux boot kernel, it is smaller than EDK2, including the Linux boot kernel. We're not currently compressing it very well, so it would be bigger. But that's something that can be addressed.
And in future, you're planning to remove the EDK2 stuff, or are you going to?
So that's, as of today, we're booting Linux without any EDK2.
Okay.
But in the future, you could move towards using the payload package and potentially completely getting rid of the shim. And then that would generate your EDK2 or UEFI interfaces, I should say.
Okay. So. Your demo, you want to talk about what you done?
Yeah, so on the demo, we can get back to it. Yeah, so this is booting OpenSUSE with coreboot, the shim, LinuxBoot, no EDK2. And it has ACPI and SMBIOS support.
Any other questions?
Oops.
Not good. Thank you.
Thank you.